Okay. Although we covered many differential equations, it's when it comes to actually solving a differential equation for engineering purposes, in most cases you will end up with some differential equation where you can't solve by hand, so you have to use the computer to find the solution numerically. Okay? I mean, this one you can solve by hand by using method of unseen coefficients, but in general, you will have to resort to using a computer to solve it. Now, when I say using a computer to solve it, I mean that you want to find the solution numerically. So you have the solution written in terms of, say, power series. That means you can't use an infinite series. What do? So you chop off the infinite series to, say, use the first 100 terms and use that as the numerical representation of the actual solution, right? In other cases, there are ways to figure out the value of the function at discrete points by using some method called finite difference method. And there's also other things like something called Runge-Kutta method. These are some of the things that you're going to learn in your engineering courses. These are numerical methods. Okay. Huh?
Is it a U?
Runge-Kutta. Yeah, I think that's the spelling. Yeah. Two
Trying to figure that
two
out.
people.
Give me a call when I figure it out.
So, but the problem with this is often the numerical method that you're trying to use happens to work on only differential equations with just a single derivative. It doesn't work on differential equations with two or more derivatives. There are numerical methods like that. So how do you repackage this given equation so that it becomes, it has only one derivative rather than two? That will be something that you'll be doing when you apply numerical method in your engineering courses. Okay? So let me show you how that's done. So, and this is called transforming a higher order differential equation into a system of first order equations. So let me show you how it's done. First, you say that y1 is y, as before. Okay? And then you say y2 is y prime. So if you call y prime as another function, what would that achieve? It will achieve the following effect. Y double prime is like taking y prime and differentiating once, and that means y prime, since y prime we renamed it as y2, now it becomes y2 prime. Right? So having this kind of renaming has the effect of only using one derivative to talk about the second derivative. Okay. Now let's go on further to see, I mean, this is always true. This is always true. But let's try to see how this change of naming can be applied to give an equivalent system for this one. So let's see. Y double prime, as I said over here, this is y2 prime. And minus 2, y prime is named y2. Plus 3, y is called y1. x squared plus 5x as before. And now you see only one derivative, right? At the cost of having two functions rather than one. Right? Now, just like usual algebraic equations, same principle applies to equate differential equations with more than one function. So let me talk about algebraic equations. If you have two unknowns, say x and y, how many equations would you need? Two equations, right? If you had three unknowns, you would need three equations at least, right? So same principle applies here. If you are trying to solve this differential equation, this is not enough because you have two unknown functions, y1 and y2. Therefore, you would need a second equation that describes the relationship between y1 and y2. And if you go back and read this carefully, you see that there is indeed something that describes the relationship between y1 and y2. See, y1 and y2 are not completely different things. What are those? How are they related? What we are calling y1 is really y itself, and what we are calling y2 is really the derivative of y. Right? Therefore, I think every time you have this, there's always this equation holding between the two, which is y2 is y1 prime. Isn't that right? Agreed? y1 prime is y2, isn't it? Okay. So this will always be added into the equation that you have. So let's write it down. y2 equals to y1 prime. And now you have a system of first order differential equations. See, I only see one derivative each. So these are first order differential equations at the cost of having two functions rather than one. So that's the process of reducing the order. So the order before was the second order, now it's the first order. Right? And you do it by introducing systems. And when do you get to use this? Not in this course, but later in the other courses where you have to use numerical solutions. Right? Now let me show you another example. Oh, by the way, usually when you write down systems, you don't write in this form. You usually write in the format where you have y1 prime equals and y2 prime equals. So let's rewrite the equation you have in this form. So first, y1 prime is here, and y1 prime is simply y2. Right? And then y2 prime is here, and if I want y2 prime equal, I should move everything to the other side. So it's really 3y1 goes to the other side, it becomes negative 3y1. Negative 2y2 goes to the other side, it becomes 2y2, and then plus x squared plus 5x. So that's the usual format that this is written. Okay. All right. Not only you can reduce the order of a second order differential equation, you can also do the same thing for third order. So let me write down an equation in third order. So maybe I should write this as a format of a question example. Rewrite the differential equation as a system of first order differential equations. Okay? And the equation given here is y triple prime minus 3y double prime plus 2y prime minus y equals to, say, 0. Suppose you're given this. How are you going to write this as system of first order differential equations? And the idea is similar. If you have three derivatives, how many functions do you want to use? Three. So you just say y1 is y itself. y2 is? What's the natural one? y2 is?
Y prime.
Y prime. Right? y3 is?
Y double prime.
Y double prime. And you stop right here. Okay? So that's the that's the convention that you have, right? Then immediately this means that y triple prime is what?
Y3 prime.
Y3 prime. See? And this is a good accomplishment. You've represented the third order derivative into first order derivative. And then you can now rewrite everything in terms of this. Okay, so using this, I can rewrite that as y3 prime minus 3, and then now you just use this, okay? So you say this is y2 plus 2y, no, sorry, this is y3, 2y2 minus y1 equal to 0. And this is nice, you have a first order differential equation. However, this is not a system and something's lacking, right? We have y1, y2, y3, 3 unknown functions. So how many equations are you supposed to have? 3. We only have 1, so how many more? 2 more, okay. Can you tell me what are the other 2 equations? Just by looking at this.
y2 prime is equal to
Actually, it's the other way, isn't it?
y1 prime.
Yeah, so y1 prime is y2. Right? What else?
y2 prime is
Yes.
equal to y3.
Y2 prime is equal to y3. Perfect. Now I have 3 equations, right? Yeah. And then finally, what you need to do is you want to rewrite it so that y1 prime, y2 prime, y3 prime. See, when you're trying to use Runge-Kutta, usually you want the equation in this format. Okay, so you write it in this format. Just rewrite all the things that you have. Y1 prime is y2, y2 prime is y3, and y3 prime is, you have to move the other things to the other side. So y1 goes to the other side, that's y1, minus 2y2, plus 3y3. Got it. Good type.